So we know that fMRI signals don't only reflect neural activity, but also co-vary with systemic physiological processes that can modulate hemodynamics in the brain. And for example, natural changes in the rate and the depth of breathing, changes in the heart rate, as well as slow hemodynamic oscillations measured at the finger and the toe have been shown to correlate with fMRI signals. And so we'd like to be able to take these effects into account when we look at our data. And in order to do that, it helps us to acquire peripheral physiological measures during the scan to use as a reference. Typically, we use a belt to monitor respiration and pulse oximetry to measure cardiac-related activity. And using this PPG data, with fMRI, we typically only focus on the timing of these heartbeats in order to correct for pulsation artifacts or to monitor the heart rate. But the signal may also contain other interesting parameters here, such as the variation in the peak-to-peak amplitude or pulse wave amplitude. And these are thought to relate to changes in cardiac stroke volume as well as changes in autonomic activity, where if you see a drop in the PPG signal, it may indicate vasoconstriction that corresponds with increases in sympathetic tone. And for example, it's been shown that, this is like early paper from the 50s, that transient arousals during sleep or drowsiness, which you can see in the EEG signal, can also come together with a sharp decrease in this pulse wave amplitude. But not just during sleep, but also in wakefulness. If there's a startling stimuli or something stressful, it's also been shown to cause these dips in this pulse wave amplitude. So then what about the fMRI correlates of this? This hasn't been investigated by too many groups so far, but there have been several studies, one of them back in 2010, and it's been shown that the signal can actually have strong and widespread correlations in the fMRI data. And in Jonathan Power's recent neuroimage study, you can also see that when he has these sharp drops in the pulse wave amplitude, that it also seems to be linked closely with changes in the bold fMRI signals. And consistent with this, we've also done some recent studies during stage 2 sleep as well as wakeful but drowsy resting state, and basically have found that changes in this pulse wave amplitude come with this spatiotemporal pattern where there's an earlier signal change in the white matter or deep white matter in ventricles with more of a bipolar dynamics and a more lagged and opposite response in the gray matter. And so one potential reason this might occur is suggested in this study, which is that since the pedal vasculature is densely innervated by sympathetic nerves, that this might come from vasoconstriction in brain that's linked with sympathetic tone. And so, and also it's important to note for the later results that this comes from a cross-correlation analysis with pulse wave amplitude. So if we're going to talk about drops in that signal, then these maps are basically inverted in sign. And so around the same time that we were doing those studies, I was looking at some data with sparse auditory tones, and I noticed that every once in a while there would be these tones that seemed to be followed by this dip in this pulse wave amplitude, and especially if it came after a pretty long interstimulus interval. So we wondered if perhaps this tone was a little bit startling and salient to the subject. They weren't very loud, but they were just very sparse. So we thought maybe this PPG dip could also signify this transient autonomic response. And so basically the idea was to investigate that just a little more. And so we were interested in seeing how much this might occur across the data set, as well as when that happens, what is the impact on the fMRI task activation. The data set was, we scanned human subjects at 3T, and these are going to be based on 10 scans acquired from 6 different subjects. And these were long multi-echo fMRI scans where we had sparse auditory tones presented while they were closing their eyes, and they were also asked to make a button press, which I forgot to rate. And physiological monitoring we carried out with the respiration belt and pulse oximetry. And we also removed, in addition to doing multi-echo ICA denoising, we removed low-order polynomial trends as well as rigid body motion parameters. Based on the raw physiological waveforms, we then also derived 3 measures of interest. So the pulse wave amplitude, which is calculated as this peak to trough distance of each pulse wave, the respiration variation or volume per unit time based on Rasmus-Burns' original study by taking the peak to trough distance of each breath divided by the distance between successive peaks, and a heart rate based on the mean interbeat interval in 6-second sliding windows. And then just to facilitate the comparison between these signals, we just resampled these all to the same sampling grid of 200 milliseconds. So first we wanted to just see on average whether presenting this tone was linked with a physiological response. So what I did here was to just make tone-locked averages for each of these physiological measures, this pulse wave amplitude, RVT, and heart rate. And so time 0 is when the tone is presented. And yeah, you can see on average there's like a little response. So a tiny dip in the pulse wave amplitude about 5 seconds later, and also a transient responses in the RVT as well as the heart rate. And so then I thought to select just the set of stimuli where there was a more substantial response in the pulse wave amplitude. So I just set up a criteria based on having the minimum value in this window 4 to 7 seconds be at least half of what it was in this earlier 0 to 3 second window. So if you just select for that subset of events, of course, this is what we're selecting for, so you see a large change in this pulse wave amplitude, but you also see corresponding changes in the RVT and the heart rate. So these tend to be coupled, which I'll talk more about soon. So then we can ask about what happens in the fMRI data. So if we first consider the case where we're averaging over every single event, our fMRI responses look like we might expect. So these are just different slices. The auditory tone is presented at time 0, and this is just over time what this pattern of responses looks like. So you can see bilateral auditory cortex and about a hemodynamic response delay. But if we average only the set of events with the substantial physiological responses, there's much more going on here. So you see these stronger initial positive responses, a lot of salience network, and then these lagged negative responses with an opposite sign in the ventricles and deep white matter. And so that's consistent with things that we and others have seen before. And then, of course, if you also just take the complement, the remaining trials that didn't have these pulse wave amplitude dips, then again, it looks much more like the canonical task response that we'd expect. And so then, so these, I'm just putting back what I showed before, which is when we had selected for the events with the PPG dip. And then if you look at the ones that didn't have the dips, they also don't have much RVT or heart rate. So emphasizing that these waveforms tend to just be quite coupled. And that's not so surprising given that there are known dependencies between these measures and the autonomic processes that generate them. And on average, I tend to see very strong correlations between this pulse wave amplitude and RVT. And in addition, this work agrees with a previous study, or actually this is a current study that's studying the respiration, dynamics of the respiration or RVT responses. And so if you just turn those maps that I made kind of sideways, it's exactly the same representation. And these were, this is a response to RVT derived in the resting state scans from the Human Connectome Project. So at this point, one question may arise as to what kind of mechanism is generating the bold or fMRI response pattern that we see. So one possibility is that in part it may be due to autonomic effects linked with vasoconstriction as hypothesized in the one study I mentioned. But it might also be, of course, due to changes in arterial CO2, which can also be modulated by breathing. And this data set does not allow us to clearly resolve those mechanisms there. But one thing I noticed was that not all of the times that we saw this pulse wave amplitude drop was there a noticeable response in respiration. Sometimes it was very subtle. So like here, there was a drop in the pulse wave, but just a very subtle change in the respiration. And so I just screened for events where this was the case just to see what happened. And it turned out that there weren't very many at all. I mean, it was a very small number. So what I ended up doing was just relaxing the criteria a little bit to say, if we see a drop in the pulse wave amplitude, but there's only up to 25% increase in the RVT, what happens if we look over these trials in the fMRI data? And so basically that's over here. So even if we do limit the RVT change, then you end up seeing quite a similar pattern as you do with all the physiology. together. And this is not conclusive because it definitely needs to be more quantitative if we want to draw better conclusions from that. But it did suggest to us that this pattern might originate in it, at least in some part, from this sympathetically mediated changes in vascular tone. So here we looked at the stimulus-evoked physiological responses, which were found to produce this spatiotemporal pattern, which closely resembles those which have been pointed out before in sleep, resting state, as well as task-correlated breathing, especially with the negative cortical changes. And also to temporal ICA study, finding a very widespread or global light component that resembles these maps. And that fact that we found this even with some limited change in respiration does suggest that there's some partial contribution from this sympathetically mediated vascular tone change, but that needs to be followed up in future work. And finally, since the activation maps look different depending on whether there was a concurrent physiological response, which was also motivation for studying this to begin with, since some of the maps did look so different, these results do emphasize the importance of accounting for these physiological effects in task data and not only in a resting state, and especially if you think that the task may elicit some kind of surprised or startled reaction. So I'd like to say big thanks to my colleagues at NIH where this work was carried out, and thank you for your attention.